I finish this problem. So actually, since Serdar's not on, do you guys want to take a look at this one?
Yeah.
Okay.
We could do it. Yeah.
All right.
Yeah, let's do this one first.
Okay. So we have a triangle ABC with circumcircle K centered at O. So yeah, this, let's see. Oh yeah, definitely. And then the tangent, okay, really, it's better if C is at the top. So BC should be greater than AC. So actually, let me do it like this, kind of like it like this. The tangent at C intersects AB at D. Yeah, the Gulf, those problems for the Gulf Math Olympiad were like easier than for the other team selection tests, it looks like. So here's point D. The circumcircles of BCD, OCD, and AOB. Okay, so that's a lot of circles. So BCD, OCD, I'm going to draw this a little better, and AOB. So we want to see where they intersect the ray CA. Now this looks tricky. Kind of like this. I kind of like this diagram actually. It looks fun. So let me just make this a little straighter. Kind of like that. So BCD, that intersects it at Q. OCD intersects it at P, and AOB intersects it at K. So P is on AK and K is on PQ. That looks good. Okay, so they're in that order, APKQ. There we go. PD intersects the circumcircle of BKQ. There's a lot of circles here. At point T. And we want to show that T, that doesn't look right. Let me see if I did everything right. PD. P and T are in different half planes. I don't know if that's what's causing the problem, but let's see. So I want this to be T. Let's see if I went wrong somewhere. But yeah, it looks like, okay, so yeah, I don't want to make it look like these all concur, but something like that. So let's see where I went wrong. So P and T need to be in different half planes. So that's one issue. Because right now they're not. Oh, I think maybe they want it to be like this or something. Let's see. Yeah, it's hard to make P and T on opposite sides of BQ. Yeah, what if I draw it more like this? So the circumcircles of BCD, OCD, AOB. Oh, that's the problem. I can't really draw it like this because I need AOB to intersect the ray CA.
And T is another intersection with the circle.
T.
Down.
Sorry, say that one more time.
Another intersection PD with the circle BQK.
BQK. Okay. So oh, there's another intersection point. You're right. That's why I got confused. I forgot that there's actually two intersection points. Thanks for pointing that out. Otherwise, I might have gotten stuck for a very long time. So this right here is point T. And now it makes more sense. We want to show TB equals TQ. Thanks for that. Yeah. All right. So
DC is equal to DQ.
Whoops. DC is equal to DQ. Interesting. Okay.
That is an angle chase.
Let me hide that and hide this. Okay, so you're saying DC equals DQ. Let's see, P is
what is the use of point K?
Because we need to see where the line PD intersects the circumcircle of BKQ at point T.
Oh, okay. I drew it wrong.
Yeah, this is a really interesting diagram. Circles like all over the place. I like it though.
And do you understand why DC is equal to DQ?
DC and DQ. So let me see if I can think about the angle chase. So, because angle DCA, because it's tangent, that's equal to angle CBD, which is CQD. That makes sense. It's a good observation. I wonder if I was going to say maybe angle CDQ and QTB add up to 180, but that doesn't look true. Yeah, sure. DC equals DQ. So yeah. One sec, I'll be right back. All right, I'm back.
I'm just guessing, but I think that TB and TQ are the two tangent line to the circumcircle of BCD.
Interesting.
I'm
So
just guessing. I'm just guessing. Can you check for me?
yeah, it looks like it. Let me move stuff around a little bit, but I think you're right. Yeah, no, it looks like it's definitely true. So then we could try to do an angle chase to show angle TQC is equal to CDQ.
Oh, then that circle QKB passes through the center of DCB.
DCB. So interesting.
And also, what I think is true is that that point lies on KO.
Interesting. Okay.
Oh, so we need to prove KC equals KB, then we are done. So
KC.
according to what Stefan said.
Yeah, it looks like KO would be like the perpendicular bisector next. Okay, so yeah, we need to show
We need
KC
to
equals
prove that.
KB. It's a good observation.
If we can say KB, KT, KQ, and KO are harmonic, we are good
J.
because بله what?
So what were the four things that you said were harmonic?
Yes, KB, KT, KQ, KO.
Okay. But you said J. So
No.
E JT. So T P Q.
KO is an angle bisector, and QKB.
Okay. So I think so KQ, KT, KO, KB.
Can we prove that KC is equal to KB?
I'm not sure yet how to do that. If someone else knows.
That is an angle chase, I think. Just
Okay. So yeah, I think what Khosrow was saying is like, yeah, can we show TQEB is harmonic? So yeah, I'm just trying to get, so we want to show TB equals TQ. One way to do that is to show they're both tangent, right? How did we get from that to trying to show that this was isosceles, or that? So, Stefan, you mentioned that E lies on this circle, right? How did you, oh, because angle TQ, because if they're really tangent, then angle TQE would be 90 and angle TBE would be 90. So that's kind of how you saw that, right?
Yeah, and because
Yeah.
angle trace that KC is equal to KB, then we actually know that the center of a DCB lies on KO.
Okay, so we know that E lies on KO.
But we don't know that it lies on that circle, I think, yet.
We don't know yet that E lies on this circle.
Yeah.
Okay.
How do you define E?
E is the center of the circle BCB.
E line the circle, just use angle J because angle QEB is twice of QCB,
Okay.
which is AOB, and which is QKB. So QKEB is cyclic.
Okay. So that proves that it lies on this circle. So, okay, so then we know both facts. We know E lies on this circle, and we also know that these are collinear.
Yeah. It must be collinear. Because let's say angle AKO is equal to angle ABO, right?
AKO, ABO. Yeah, AKO is ABO.
No, sorry.
Sorry.
No. So angle KBC is equal to angle KBO plus angle OBC, and KBO is equal to OAC.
Okay.
Which is OCA, and OBC is OCB. So angle, yeah. So KCB will equal to KBC, and KO is the angle bisector. So KO will be the attitude, of course.
So you said KBC is KBO plus OBC?
Yeah.
And KBO is the same as
CAO.
CAO. So yeah, that, which is OCA. I like that. So yeah, so that's how we know it's isosceles. Okay.
I think we need P is the midpoint of QA.
Interesting.
Yeah, we need P is the midpoint of QA. It must be the midpoint. Yeah.
It almost looks like that's probably a coincidence, but yeah, do these concur? I doubt it. Let's see. Oh, it looks like they do. Oh, that's weird.
And that concurrency point should be the C median, like
This is the median of CBD, right?
the C median of ACBD.
Oh, of ABC.
Yeah.
And is are A, E, and F collinear or C, E, and F? I don't think no. I wonder if this is the midpoint of AB.
Yeah, it is the midpoint. Yeah, so P is the midpoint of AQ, of course, because the circle OCD is have the diameter DO, and if G is the midpoint, so OG will be OG will be perpendicular to DG. So
Okay.
yeah. So let's say I will prove P is the midpoint of AQ.
Okay.
So AD times AG is equal to AP times AC,
Mm-hmm.
and AG is a half of AB. AP is a half, but AD times AB is equal to AC times AQ. So P must be the midpoint of AQ.
Okay. So
yeah.
So we use power of a point to show that P is the midpoint of AQ.
Yeah.
So what are we gonna do after that? Like if we prove,
So D is the midpoint of arc QC, right?
Or P is the mid.
So
Mhm.
D is the midpoint of arc QC, because angle CBD is equal to DCI. Yeah.
Mhm.
So DQ square will be equal to DA times DB.
Mhm.
So that triangle DAQ will be similar to triangle DQB,
Mhm.
which is that AQ is the anti-parallel of QB.
Mhm.
Yeah, but DP is the median of DAQ, so DP will be the median of DQB.
Oh, because it's the median of one, then it's a semedian of the other, and so.
And so if you let that line cut the circle at point T, it will be equal to the the T. Yeah.
This T.
Yeah. So TQ and TB will be the tension.
So I kind of see how.
Just let the tension from Q and B cut at the point T.
Mhm.
Yeah. And so from angle J, we will have T lie on the circle QKB.
Okay, so what I'm gonna do, if I hide this and I draw the two tangents, so
actually we don't need to redefine point T because later he proven that DT is the median, right? However, T lies on the circle passing through Q, B, and E.
yeah,
So it must be the intersection of the two tangents.
yes, so this is okay. So I think I see it. Okay, so I'm gonna start writing it up. So if we say, I'm reading what Kazra wrote. If we say angle EKF is 90. BC, yeah, right. So yeah, let me see where I want to start here. So I'll just say let E be, I'll start by saying let E be the center of the circle BCD.
Actually, we don't need point E.
Oh, that's true. We don't even need it. Okay.
Yeah.
I think we do because you know the C median and it cuts the circle passing through QB and the center. The center
No,
is E.
no, we don't need it. We don't need it because we just need that DB is the C median. That's all.
Hmm. So
Okay, yeah, we don't need the point E. Yeah, just do it. Yeah.
But it is important that that point lies on that circle.
So
If
I
we-
guess what I'm thinking is, if we show that QKEB is cyclic, then we'll know that this is the circle through QE and B. And so then that would mean that if this circle intersects at T, then those are tangents. So I think we need to know, like, I think we want to know that this circle passes through E, because
No, no.
then,
We don't actually need it because let's say if we call T is the intersection of two tangent from Q and B, right?
Mhm.
We just need it to belong to the circle QKB, and we can prove it by angle chase. We not actually need the point.
Okay, so basically if we let,
But he has to redefine point T, right? They're just the same. Like if you redefine point T or not, like they're the same way.
yeah, so
Yeah.
it'll pass through this point, and then you're just saying by an angle chase, we could show that QKBT is cyclic.
Yeah.
Okay, so I'll call this T prime instead. So, and then I'm going to show that QKBT prime is cyclic. So T and T prime are the same point. Okay, so then I don't need E. All right, so let the tangents to BCQ BCQ at B and Q meet at T prime. So first we're going to show that BP, so like we showed that P is the midpoint of AQ, and we did that like using power of a point. So basically, because AC times AQ was AD times AB, which was AD times 2AG. So yeah, I'm just trying to think of the order. So what did we prove first? Did we first we define G, so let G I'm just trying to remember the order of everything.
We define G is the midpoint of AB, and then we prove G lies on the circle passing through the DC and O.
Okay, through DC and O. So let G be the midpoint of AB. And then
Yeah. And OG is perpendicular to DG, so G lie on the circle.
okay, so that's a right angle, but okay, so since angle OGD is 90, but how do we know that O and D? How do we know that O? Oh, because angle OCD is 90 because it's tangent. Okay. So we have angle OCB equals angle OGD equals 90.
Do we use point F?
Maybe not. Let me hold on one sec. So that means that GOCDP is cyclic. So I guess we start like that. Yeah, so that's 90 because it's tangent. Okay, so then once we know that, we use power of a point a couple of times. So you asked, do we ever use F? I don't think so. So I'm going to delete it just for now, or hide it. So we have AC times AQ. Okay, so AC times AQ is AD times AB. Which is AD times 2AG. Which so we want to show P is the midpoint of AQ, right? And then we have AP times AC is AD times AG. And that implies that P is the midpoint of AQ. All right, so yeah, we can kind of combine these two together to get that. And then we let the tangents meet at T prime. And then this is a median of dBQ since it's a median of dAQ. So, so basically we have dAQ is similar to dBQ. That means that AQ and BQ are anti-parallel. So since DP is a median of dAQ, it's a semedian of dBQ. So and so DP and T prime are collinear. And now we want to show that that's cyclic. Should be an angle chase. So because angle BKC, let me think how to do that.
No, okay. So okay. Let's say angle BKA, BKA, yeah, is 180 minus AOB.
Mhm.
which is twice of ACB,
Mhm.
which is twice of QCB,
Okay.
which is twice of QDB.
UCB, which is twice QDB. Okay.
Yeah, and Q twice of QDB is twice of QBT.
Okay. So
Yeah, and twice of QBT is QBT plus BQT. So it would be BTQ. Yeah.
will be cyclic. Okay. So we have angle CK. So angle AKB is 180 minus AOB. Which is 180 minus twice angle ACB. Or we could say QCB, which is 180 minus 2 angle QDB. Well, actually, QCB is just QBT prime. So,
Yeah.
and which is QT prime B. And so that means that QKBT prime is cyclic. And that means that T prime equals T, and TB is equal to TQ. All right. So we could either, so this is a nice solution, by the way, that there's, I'm actually surprised we got it that fast. So let me check the chat. Okay, so we can either first try to do, so we haven't done this one yet, or this one. So we could try to do them, or we could try to do the problem that GeoKing posted. So this problem right here. Oh no, that's the one that where TB equals TQ. Let me check out this one.
I suggest we do one more and then we do this one, since you see this one has two parts and it looks a little hard. So
Okay.
maybe just, yeah, do this one first.
All right. So let me see. We can either do this one or this one.
Let's do the concurrent one.
The concurrent one. Okay.
Yeah, it's fun.
So, whoops, sorry. So we have a triangle ABC. G is the centroid. So I'm going to draw the midpoints D, E, and F, and then they concur at a point G. And obviously G lies on the Euler line, OH, and all that other stuff. And then we basically project G onto all three sides. So it's GA, GB, and GC. And then we just reflect the projections over G. All right. So this is GA. GB and GC. And then we do some reflecting. So then we get SA, SB, and SC. Oh, it almost looks like I and J lie on BC, but they shouldn't. So this is SA. Then this is SC. This is SB. We want to show that ASA, BSB, and CSC concur. Let me make this a little bigger. Let me see if I can make SB and SC a little bit higher up. There we go. It almost looks like there's some circle. Like this reminds me a little of Steinbart's theorem. So
Yeah, it reminds me too. So that's why I choose this one.
Steinbart's theorem. Is there some circle? Like it almost looks like these are, okay, they're not cyclic. Let me just check that it's true. We have ASA, BSB, CSC. Oh, that's a nice configuration.
Okay, so could you draw the the hologram? Yeah, the I don't know what to say. Reflect A over D. So yeah.
Oh, the parallelogram point.
Parallelogram, yeah. The fourth, the three parallelogram. B A C A Y A prime A B C B prime.
Yeah.
Yeah.
There actually is no word for that point. So yeah, if you couldn't think of the word, there's not really a good word for it. Hey, where is it? I thought oh, there it is. It's far away. Okay. Let's see.
Okay. First of all, let's say if you do the homotopy -1, so SA will become GA, right?
A homotopy of -1 about G.
Yeah.
Yeah, SA would become GA.
Oh no. My bad. No. Am I wrong?
Should I erase this point or should I keep it? I can keep it for now.
Yeah, okay.
Let's see, which is F and which is... Okay, really this is GC and this is F.
Oh, I think I've done it.
Okay.
So do you remember the Chauvian nest theorem?
I think vaguely, but yeah. So
Yeah, I'll recall it. I'll recall it later. So can you just label the can you draw EF?
yeah, EF.
And
I can
you,
delete. Can I delete A prime?
Yeah. You just delete A prime.
Okay. Let me zoom in a little bit just to make it look better.
Can you draw the altitude from D onto EF?
Yes. From B to EF.
From D. From
D
D.
to EF. Okay.
And let's call that point B prime or A prime. I think let's call it D prime.
D prime.
Yeah, if we can prove that ASA and D prime are collinear, then we are done.
Okay. So that's probably a homotopy. I'm sorry, go on.
Oh yeah, no. We just need to prove that.
But that's because to do that, we just have to show that AG over GSA is AD over D prime, and that's just ratios because like we know GSA is the same as GGA. So that's it's going to be 1/3 of the altitude, and we know that this is half the altitude.
Yeah,
So
you're right. That's very cool. So we have ASA and D prime are collinear. Can you just draw a line through them?
Yeah.
So we define point E prime and F prime similarly.
Mm-hmm.
And then the Chauvin's theorem said that if D prime, E prime, and F prime is concurrent, then AD prime, B E prime, and CF prime is also concurrent.
Oh, because if DD prime, EE prime, and FF prime concur, then those also have to concur, is what you're saying,
Yeah,
right?
that's what the Chauvin's nest say.
Yeah, and actually this actually shows the proof of that pretty clearly, because basically like BH over HC, it's the same as FD prime over D prime E, right? So basically, if those three, if DD prime, FF prime, and EE prime concur by Cheva, then that would mean that FD prime over D prime E, it would mean if we took those three ratios, it equals 1, right? Which would mean that BH over HC. So basically, yeah. So the Chauvin's nest theorem actually has a pretty easy proof.
That is not a proof of the whole Chauvin nest. This is just a
because we don't
special
have
case.
yeah, this is just a special case. Yeah.
Okay.
But the whole proof isn't much different than that.
Oh, because in this case, everything's parallel, so it makes it easy, right? Like EF is parallel.
The ratio are easier to calculate. So yeah, you can just write a solution.
Okay.
In the general case, you observe some signs.
You need a few more like a little bit more trigonometry or stuff like that. Yeah, I remember the proof being written on Discord. Okay, so basically, yeah, I'll just write this up quickly. We still have about an hour, so let's see. Let D prime be the foot of the perpendicular from D to EF. Define E prime and F prime similarly. I'll just say not shown. So yeah, the key idea is basically we're showing A, S, A, and B prime are collinear by showing, so you know AG over GB equals 2. That's well known. And then, well, really we want to AG over GD. AG over AD is 2/3. That's well known. And then we also can try to calculate SAG over D prime D. So we have D that's equal to GA over D prime D, which is equal to so I'll say let HA be the length of the altitude from A to BC. So GG prime, that's going to be HA over 2. Whoops. And DD prime is going to be, oh no, HA over 3. And DD prime, that's HA over 2. And so that's equal to 2/3. And so that means that ASA and D prime are collinear. So and similarly for the other sides. And then once we know that, let me hide this. So I'll just say DD prime, EE prime, and FF prime concur. And FF prime concur at the orthocenter of DF. And then we can use a Chebian's nest theorem. So by the Chebian nest theorem, AD prime, BE prime, and CF prime concur. That means that ASA, BSB, and CSC concur. Let me fix the latex. All right. Yeah, this is easier than I thought. Yeah, that was the key insight, was showing ASA and D are collinear. So let's see what the problem was on Discord. So the solution might pop up really quickly. So actually, you know what? I'm just gonna stop sharing really quickly so that you guys don't see the solution to it, and then I'm gonna share it again once I paste it into. Okay, so it's, oh, actually, I gotta look up the problem on AOP. So it's 2010 Balkan Shortlist. Let's see. gonna go to contests, 2010 Balkan Math Olympiad Shortlist. Come on, come on. Okay, but I need to find the shortlist, not the actual contest. So I will check that out. Shortlists. Here we go, 2010. And it's geometry. An ABCB triangle and LB. Oh. Okay, so here it is. Paste it in. Oh, okay, I can share it because no one actually solved it on AOPS, so you guys won't see the solution if I pull it up. So here's the problem. Let's paste it in. A copy. And then paste it. So this is Balkan Math Olympiad Shortlist 2010. All right. So we have a ABC. There we go. Let's see how this turns up. Not too bad. Let me just do it like this. There we go. So we have a triangle ABC and we have a line L. Okay, so at least one of the sides we need to extend. So BC, I'm going to draw the whole line. And okay, so this is, so it meets it in A1, B1, and C1. And then this is B1 and C1. And then A prime is the midpoint of the segment connecting the projections of A1. Okay. So this is a little bit tricky. You really have to draw all the. Okay, so basically you draw the perpendiculars from A1 to those two, and then the midpoint of it. So is that just the center? So that's just the center of this circle, because there's a circle through those 4 points. Yeah, so if we want,
it isn't the center of the circle.
oh no, you're right, it's not the center of the circle. That would be the midpoint of A1, which should be different. Let's see. Yeah. Okay, so there's one midpoint. And what do we call it? We call that A prime. And then let's do this with B1. So yeah, this is kind of a complicated diagram. So BC and BA. Let's see if I can make this a little better. There we go. So we got this, that point, and then I want the midpoint. So that would be B prime. And then I do the same with C1. So I drop perpendiculars onto BC and AC. And then I take the midpoint. This didn't turn out as bad as I thought it might have. It's still messy, but I thought maybe it would be even more messy than this. So we want to show that A prime, B prime, and C prime are collinear. All right, let me hide a whole bunch of stuff here. I'm going to hide almost every line there is and then redraw stuff. Oops.
There's hiding tools that you could use. Yeah.
Just hide it. Yeah, you're right. This I don't think I need to hide. Okay. All right. So this. Wait. So I draw that perpendicular. Yeah, I don't think I don't think I need A1A. See, someone wrote something in the chat. Yeah, this wasn't as bad as I thought. It's still messy, but maybe not super bad. Let me, I think I could probably make it look better if I and G are farther away. Yeah, let me make it, maybe that looks better. So yeah, with B1 and C1, we can kind of see what's going on. You take the perpendiculars in the midpoint, and then for A1, it's a little bit awkward, but it's okay. It's intended to be bashed. One sec, I'll be right back. All right, I am back. So let's see. I wonder if
Oh,
there's
it
some
looks like the circles with the diameters AA1, BB1, and CC1 are coaxial.
coaxial. Okay. So I'm going to draw those.
Oh, that is actually the Gauss line.
Oh, okay.
From the Gauss line. Yeah, that is. Yeah.
So the Gauss line.
Or not that point. BB1 and G, not BB1 and A. Yeah.
Yeah, that was the wrong point. But isn't the Gauss line like, is that the Gauss line of HGIF? Because you have one midpoint. Like what's the quadrilateral that is the?
I mean, that is not literally the Gauss line, but it is connected to the Gauss line.
Okay.
That is the like Steiner line or something like that. It is
Okay.
perpendicular to the Gauss line of BC, B1, C1.
BC, B1, C1. Okay. So. So wait, are you saying if I take this midpoint and this midpoint? Okay, it's not.
Just right. Yeah, maybe we could use them.
Oh, draw those two midpoints.
Yeah, in midpoint of A1 as well.
Okay. So those are the centers of the circles, right?
Yeah. And could you draw? Yeah, that line. Yeah.
And then so yeah, I forget for the proof of like one of the proofs of the Gauss line, you show that the three circles are coaxial. So this isn't exactly the same configuration, but is it like the same kind of proof? I guess is it obvious that these are coaxial?
We use the radical axis. It is a special line. It's called a Steiner line. It passes through two orthocenters
Okay.
of the triangles, but I don't remember exactly which one.
Okay.
They must be coaxials because the three center is collinear, so they must be coaxial.
Actually, if the centers are collinear, we are not sure that if they are coaxial or not, because the radical axis can be parallel to each other.
Yeah, like you could still have, like for example, like what if one of these circles just had a smaller radius, right? Like just because the three centers are collinear doesn't mean that they're coaxial. You need like one more piece of information, I guess. Yeah, part B looks pretty hard. Although this was a long time ago, so I don't know. So basically, you guys think part A is like well known, right? That's kind of what you're saying, right?
Actually, we haven't proved it yet.
Okay.
Why is part A well known?
Oh, okay. Then part A is not well known, but the fact that these are coaxial, is that well known?
Probably.
Probably.
Yeah,
I don't know. I haven't heard of
yeah,
one.
there's even a name to that radical axis.
It's true by the radical axis theorem.
No, I mean, we proved they share the same radical axis, and there's even a name to that radical axis.
Okay. So that is well known. The fact that they all have the same radical axis.
Yeah. Well, wait, you haven't done any video about this yet? It's called the Steiner line.
No, I did a video on like the Gauss line. So like I did a video where if you just start with like any quadrilateral and you like extend the sides to meet, let me see, how should I do this? So here's what I did a video on. So if you have this point, and this point, basically if you take the midpoints of these two diagonals, and then you take the midpoint of QR, those 3 points are collinear. And I didn't put this in my video, but basically, so if you have this midpoint, this midpoint, this midpoint, ST and U are collinear. So that, I proved that in my video, that ST and U are collinear. Then there's another theorem which says, and this is like another way to prove it. It's not how I proved it in that video, but if you have this circle, and this circle, then they have the same radical axis. So, yeah, how do I make them intersect there? Yeah, you can see how those three circles have the same radical axis, right? But I don't see how this proves it in this case. So is this like the fact that these three are coaxial, is that like a generalization of this idea?
Actually, it's just two different ways to prove the Gauss line.
Okay.
I think the other way that you're saying is using Menelaus, right? What did you use?
Oh, I actually didn't do it either. I didn't do it using this way, and I didn't do it using Menelaus. I actually did it using areas, like, so it's kind of interesting.
Okay, so there's 3 ways to prove it.
Yeah, 3 ways to prove the Gauss line. Yeah.
Maybe we can mimic the way that we prove the Gauss line for this one, maybe, or just.
Yeah.
I don't know, but it seems a little, similar.
Okay. Let's see. So I'm trying to remember the way I proved this in my video. So I think every point on the line ST, the sum of the areas of SMP and SNO are the same. So like, yeah, so here's the thing, like, so if you take the area of SMP plus the area of SNO, it's half the area of this quadrilateral. And the same thing's true with point T. And then it's not hard to show from that the same thing's true with every point on the Gauss line. So the area for every point on this line, but the thing is, if the point lies outside the quadrilateral, then you have to like subtract the areas instead of adding them. But that's kind of the idea that I used. So I wonder, maybe there could be a way to do it here. I'm not sure yet.
I know one theory that I think can help us in this problem. Can I say?
Yeah, sure.
In the NOPM, and choose 2 points, one of them on NM and one of them on OP. With this that are.
So one of them, you just choose a point on NM and another one on OP.
Yes. And we must have NM on NV on VM equal to OW on WP, and we have midpoint of NO and VW and midpoint of MPR collinear.
Oh, really? If those ratios are the same, so NV over VM is OW over WP?
Yeah.
Interesting.
That theorem called ERIQ.
Yeah, the ERIQ lemma.
The PRIQ lemma. Interesting.
ERIQ, yeah,
ERIQ.
yeah, like that.
I never heard of that.
I
Okay.
was finding a way to apply to the part A, but there was no quadrilateral.
Interesting. Okay. So what if we let GI intersect BC? It's going to be far away. Basically, if GI intersected BC at a point, let me see if I can make it like easier to see, then basically if we take the midpoint of DZ, I guess I can delete this for now. Hey, what just happened? Oh, I must have deleted that line. So B prime, C prime, and the midpoint of DM. These would have to be collinear by the Gauss line. I don't think this line passes through it here. Oh, it almost looks, is that a coincidence? I don't think that always happens. No. So, but this line will, the line through A prime, B prime, and C prime. Wait, that almost doesn't. Oh, no, because I need to see where FI, no, that one, that's not right. I'd have to take where HG and FI intersect. So yeah, that doesn't work. Yeah, this looks hard. We can look at it for another 5 minutes, then I could try to check out the other problem. So wait, these 2 points shouldn't be exactly the same, should they? Huh. Oh, because let's see. Okay, so for part, I'm just curious about part B. I know we haven't really solved part A, but like what if instead of considering these 3 circles, we considered the circles with centered at A prime, B prime, and C prime. So
Yeah, those are not coaxial. I tried doing that before.
okay, they're not coaxial. I wonder do they no, that's no way those concur.
Wait, how about we prove the radical axis of them are parallel?
We could try that.
Yeah, but I think it's hard to determine the radical axis.
Yeah. Yeah, no, it's hard to figure out what the radical axis is. I think it's, yeah, better to draw the other circles. All right, you guys want to check out the other problem? Let's see. Yeah, I agree. Let's try the next one. So this one, we have a triangle ABC. D is the midpoint of BC. And E is the intersection of the angle bisector with BC. So I'm going to draw both of them. Here we have D, E, the perpendicular bisector of AE. intersects the bisectors of CBA and CBA. CBA, so that's not really symmetric. CBA and CBA. At M and N. So I'm going to label this point. So this is M, and this is N. And then we draw the bisectors of CBA and CDA intersect at P. Okay, so like all three intersections of those. And we want to show A, M, N, and P are cyclic. That's an interesting problem. All right, so let me make it bigger, make it look nicer. It almost, I don't think AP is parallel to BC. No. Okay, so we have AE's angle bisector. And then we draw the perpendicular bisector. And we see where it meets this bisector and this bisector. So, an interesting configuration. Is there any other special point that the circle goes through? Not that I see. Is AD tangent to the circle? Let's see. Yeah, it looks like AD, oh no, it can intersect it. So AD is not necessarily tangent. Is AE? No, AE doesn't look tangent. So how would we prove it's cyclic? Should we let AP and MN intersect at a point? So yeah, we power of a point. I wonder if there's anything special about the center of that circle. Are F, M, and D collinear?
We have AM, EB is cyclic.
AM, ED?
EB.
AM, EB. Okay, that's probably a good way to start.
Yeah, this is trivial. It's really easy to see.
Okay. Because yeah, if we could show MA equals ME, yeah, it's trivial. Yeah. All right. So do we have an X? So P is the X center of ABB. So maybe it's worth drawing like the X circle. Wait, sorry. So I did something wrong here. Oh, ABD. Yeah, okay. I should have drawn the perpendicular to AD instead. So wait a sec. Yeah, like that. There we go. So I don't. Yeah, so P is the X center. Maybe we could use like the in-center X-center lemma. So, whoops. No, that doesn't look right. Oh, because M is the midpoint of arc ABE, of the triangle ABE, but P is the X center of ABD. That's what makes it look weird.
I think we haven't used the fact that D is the midpoint of BC.
Yeah, we have to use that somewhere, you're right.
ANED is cyclic.
AMED, is that what you said?
ANED.
Ah, okay. Interesting. We know that. Is there an angle chase that can sort of finish it? It almost looks like G and DE is cyclic, but
How do we prove ANED cyclic?
is GMED, or why don't we prove what's cyclic?
He said that ANDE is cyclic.
Yeah,
How do we prove that?
because it is obvious because DN is the angle bisector of ADC, which is ADE. and GN is the perpendicular bisector. So they are cyclic.
Okay, because
Oh,
we have
I think this is actually finishes the problem with an angle chase.
okay.
Like, let me just tell the angle chase and see if it is good or not, because
Okay.
it looks a bit suspicious.
Okay.
Angle AND,
Mhm.
that is equal to AEB,
Okay.
and that is equal to AMB.
Okay.
And then that should be it, actually, because then we prove that AMP and
ANP. Yeah.
But does this use the fact that this is a midpoint?
Okay, so let's see. So we have AND is equal to AEB, which is AMB. Yeah, where did we use that? Well, we have to prove that ANDE is cyclic, so we'd have to use the midpoint there. So yeah, how did you know that ANDE is cyclic? So I think Dat mentioned it, because this is like a perpendicular bisector.
I think it is because of the bisector. And also because NA is equal to NE.
MA is equal to ME. So, but yeah, how exactly do we prove that?
Yeah. If you let the angle bisector of ADC cut the circumcircle of AED at point N, so N will be the midpoint of arc ADE.
So I let the angle bisector of this angle. So like this point right here.
No. ACD. Yeah.
ACB. So the angle bisector.
ADC. ADC.
Okay.
Yeah, cut at the point N prime. So N prime will be the midpoint of arc AE.
Oh, that makes sense. So that proves that it's cyclic. Okay.
Yeah.
So
I think that this problem is it doesn't matter that M is the midpoint, D is the midpoint, because I now drew another picture where I let D be a variable point and it looks cyclic all the time.
interesting.
I think this is an arbitrary point line on BC.
So they gave us more information than we needed. Okay. So okay, so let the angle bisector of ABC. I could type it up really quick. Meet the circle AED at N prime. Then we could just say by an angle chase, N prime is the midpoint of arc AE. Wait, is that? So you're saying N prime would be the midpoint of arc AE, the big arc AE?
Yeah.
Okay. We'll just say major arc. And so that basically means N prime is equal to N. So that means that AEDN is cyclic. So did we even use, something's weird, because, okay, let me just write this out. But
Yeah, I think we don't even use the fact that P is the intersection of the bisector.
Yeah, like, can this line be any line? Like, let's see.
So,
So
like, E and D are like arbitrary.
D and E are well, so D and P are kind of both arbitrary.
No, P is the intersection of the angle bisector of ABC and
The line BN.
Perpendicular bisector of AE.
Okay. So first we define point M, and then yeah, so we define M and N. But yeah, D can be whatever it wants. So wait, first I'm going to write out, so we have angle AND equals AEB. Which is equal to AMB and that means angle AMP equals angle ANP. Which means that AMNP is cyclic. But is it? Let me see. So is there anything I left out here? For the circle ADE, the outside bisector of ABE cuts the circle at N. So N is the midpoint of arc AB. Yeah, okay, because basically yeah, so that makes sense. So is this the whole proof right here? Where did we use that this is an angle bisector? Oh, in order to show AMEB is cyclic. So yeah, so I didn't write that out yet. So yeah, M is the intersection of the angle bisector of ABC, or I'll say ABE, with the perp bisector of AE. And so that implies ABEM is cyclic. Okay, so yeah, that was that last step. All right, so that sounds good. So so we finished this problem. I didn't need to use that P was the X center. So I think we're gonna stop here. So for everyone watching on YouTube, thanks for watching. And I want to thank everyone on this session for participating, sticking around for so long and helping support my channel. So if you want to join future sessions, feel free to email me at mgreenb801@gmail.com. The email is going to be in the description of my video. And we do this every Sunday at 8 a.m. US Central Time. Thanks for watching and have a good day.